Hey Global Impact, this is Mr. Ellinger. This lesson is on the probability of multiple events. Our learning targets for the lesson are to find the probability of the event A and B, find the probability of the event A or B. Essential understanding: to find the probability of two events occurring together, it is necessary to determine whether the occurrence of one event affects the probability that the other event will occur. Okay, so what we're talking about here is we're talking about whether we're working with independent or dependent events. And in algebra, we'll talk about, we talk about independent variables versus dependent variables. And the same logic behind those two expressions follows here with independent and dependent events. To find the probability of two events occurring together, you have to decide whether one event occurring affects the other event. When the occurrence of one event affects how a second event can occur, the events are dependent events. Otherwise, the events are independent events. So, an example, you select a coin at random from your pocket. You replace the coin and select again. Are your selections independent events? So you have some coins in your pocket. You pull a coin out, put the coin back in, pull another coin back out. If we were looking at a probability situation, would those events be independent or dependent? Well, they would be independent events because when you put the coin back, you have the same number of coins in your pocket the first time and the second time. If you were to keep that coin out on the second time you pulled a coin out of your pocket, then those would be dependent events because you wouldn't have the same number of coins in each draw out of your pocket. So does the sample space change for each coin selected? And again, the answer is yes. That's what I was just saying. The sample space will be one less coin on the second time you pull a coin out of your pocket. And every subsequent time after that, if you didn't replace the coin each time, your sample space would continue to decrease, thus changing the probability every time. And those would all be dependent events. Alright, so an example here of probability of multiple events. At a picnic, there are 10 diet drinks and 5 regular drinks. There are also 8 bags of fat-free chips and 12 bags of regular chips. If you grab a drink and bag of chips without looking, what is the probability that you get a diet drink and fat-free chips? So event A, they're saying, is picking a diet drink, and event B, they're defining to be picking fat-free chips. A and B are independent events. Picking a drink has no effect on picking the chips. So we can look at what's the probability of A and B. So what's the probability that we pick a diet drink and pick fat-free chips? So what we're going to do, the calculation we're going to do, is we're going to figure out what's the probability of A, and then we're going to multiply that by the probability of B. Okay? And here's how we would find those two probabilities. So the first probability, number of diet drinks over the total number of drinks. There's 10 diet drinks, there are 15 total drinks. There are 8 bags of fat-free chips, and there are 20 total bags of chips. If we multiply those two fractions together, we get a reduced fraction of 4 over 15, which is approximately 0.267 as a decimal, or 26.7%. So the probability that you get a diet drink and fat-free chips is about 26.7%. And what is the probability that you get regular chips and a regular drink? Well, how many regular chips are there? And how many regular drinks are there? Well, there are 12 bags of regular chips out of 20 total bags of chips. And there are 5 regular drinks out of 15 total drinks. So if we multiply those two together, we get 60 over 300, and that fraction reduces down to 1/5, which is 20%. Right? So will the probability be the same for the next person who chooses a drink and a bag of chips? This is where our independent and dependent events come into play. When another person comes through the line at the picnic, and people have already taken items, the probabilities are not going to be the same. because we're working with a fewer number of chips and a fewer number of drinks. So the answer to this is no. All right, our next topic here in this lesson, two events that cannot happen at the same time are what we call mutually exclusive events. Cannot happen at the same time. If A and B are mutually exclusive events, then the probability of A and B is 0. They can't happen at the same time. So here's an example. You roll a standard number cube, okay, our standard 6-sided die. Are these events mutually exclusive? Part A says rolling an even number and rolling a prime number. If we roll a standard die, our even numbers, we could get a 2, a 4, or a 6. Our primes, remember primes are numbers that can only be divisible by themselves. So we have a 1, we have a 2, we have a 3, we have a 5. So 2 is an even prime. So in part A, those events are not mutually exclusive. They can happen at the same time. You can roll a number that's at both an even and a prime. In part B, rolling an even number and rolling a number less than 2. Well, these are mutually exclusive, okay, because you cannot roll a number less than 2 that is also even, because 2 is the smallest even number. Here's another follow-up question dealing with mutually exclusive events. Are mutually exclusive events the same as independent events? And the answer is no. If one mutually exclusive event occurs, the other cannot occur. Period. In independent events, we just have events that they don't affect each other, but they can both occur. Mutually exclusive events cannot both occur. It's either one or the other. Right, we can make a Venn diagram to determine whether events are mutually exclusive. So if I go back to my example in A here, and I kind of did this, but if I were to draw, instead of listing these out, a Venn diagram, we know we have some universal set of items. Let's say we have one set in here that represents our evens, and we have one set in here that represents our primes. Okay, so if we put our numbers in here, we can put our evens in here. We can put 4, we can put 6. We have to put 2 here though. 5 and 3 are primes. But 2 we got to have in the overlap here of the two sets. Okay, remember that's called the intersection of two sets. Anything that's in common in both sets is what we call in the intersection. And on a Venn diagram, it's the overlap of two sets. So anything in this area is in both sets at the same time. Where does the number 1 go? Now the number 1 goes out here. Number 1 is a weird number. Technically, it's not a prime. So here's an example, some more probability. At your high school, a student can take one foreign language each term. About 37% of the students take Spanish. About 15% of the students take French. What is the probability that a student chosen at random is taking French or Spanish? So here we kind of have the thought process of what we need to do here. We have a no box, we have a need to know box, and we have a plan. So you can take a look at those. One foreign language each term means the events are mutually exclusive. Okay, that means you can't take 2 foreign languages at the same time. That's what that means. So what is the probability that you take Spanish or French? Well, we have to calculate the probability of taking Spanish, and we have to calculate the probability of taking French. And what we do is we add those 2 probabilities together when they are mutually exclusive. So the probability of Spanish is 0.37 approximately. Taking French is 0.15. Add those 2 together, we get 0.52. So the probability that a student chosen at random is taking Spanish or French is about 0.52 or 52%. In this problem, about 9% of the students take Mandarin Chinese. What is the probability that a student chosen at random is taking Spanish, French, or Mandarin Chinese? Well, again, these 3 are all mutually exclusive events. Okay, they cannot occur at the same time. So the way that we calculate the probability of this, or this, or this, okay, we're talking about or probabilities, is to add their probabilities. So from the previous example up here, we knew that the probability of Spanish or French was 0.52. So now we just need to add the probability of Mandarin Chinese, which is 9%, or 0.09, which is 0.61. So that's the answer for A. There's a 61% chance that a student chosen at random is taking either Spanish, French, or Mandarin Chinese. All right, part B, without knowing the number of students in the school in problem 4, can you determine which language most students take? Well, the answer to that is yes. The percentage of students tells which language is chosen more by students. So whichever language has the highest percentage is going to tell us the language most students take. All right. Another question here. Is it possible for 50% of the students at school to be enrolled in Latin? And the answer is no, because we know that 61% of the students are enrolled in either Spanish, French, or Mandarin Chinese. And students can only be enrolled in one language at a time. The highest percentage of students that could be in Latin would be what? 39%. 100% minus 61%. Okay, so the answer on this is no. What is the probability that a student is not taking Spanish, French, or Mandarin Chinese? You know, we talked about sets in previous math classes, and this is what's called the complement of a set. These three, think of these three as a set. If we know the probability of these three occurring, and we want to know the probability of not these three occurring, what we do is we take the number 1, which represents 100%, and we just subtract the probability of these things happening, which we know is 0.61. So when I do that calculation, I get 0.39, or 39%. So anytime you're doing a not problem, what is the probability that something is not going to happen? Do 1 minus the probability that that something does happen. Because a lot of times we will know these. And that's how we calculate the probability of not that. Okay, so when we're doing an and probability, we have to know that we're going to be multiplying probabilities. Okay, independent events, dependent events. When we're doing or probabilities, we know that we're going to add probabilities. And those are probabilities dealing with mutually exclusive events, possibly. All right, folks, have a good day.